All right, so we're going to get into chapter 9, and we're going to be talking about comparing two means. And let's see, just to remind you, we're using the free statistical software with JASP, JASP, and so let's go. So in the previous chapter, we introduced the inferential procedure of hypothesis testing. We reviewed how to conduct a hypothesis test for a single proportion using the binomial test. So that was chapter 8. Now we're in chapter 9. And in this chapter, we're going to focus on scenarios that involve means. So we can recall that we can compute the mean for variables that are at the interval or ratio level. The tests we're going to cover in chapter 9 are frequently used in psychological research. So for example, a psychologist might want to determine if stress levels differ between individuals who exercise regularly and those who do not exercise regularly. Or a psychologist might want to analyze something like memory capacity or working memory capacity. So if working memory capacity, the psychologist may want to see if the working memory capacity is affected, for example, by listening to music compared to when the participant is not listening to music. In a medical context, for example, we might investigate whether a new drug will increase or decrease blood pressure. And maybe an agricultural scientist, they might want to explore whether phosphorus to an Australian native plant will affect their survival. So in all of these example situations, our outcome variable is at the interval or ratio level, and our predictor is a binary grouping variable. So essentially, we aim to compare the means of two groups. The standard approach to comparing means is to use a t-test, which comes in several varieties depending on the specific question that we are addressing. So as a consequence, the majority of this chapter 9 will focus on the different types of t-tests. And one example, mean t-test. One sample mean t-test will be discussed in our chapter 9, section 9.2. And let's see, yes, so we're going to go over the one sample mean t-test, the two independent means t-test, and a paired samples t-test. Then later on, we're going to talk about Cohen's d, which is the standard measure of effect size for a t-test. And then at the very end of the chapter, we're going to review a few different ways to check for normality, as well as a few non-parametric tests that can be used when the assumptions for conducting a t-test are not met. However, before discussing any of these useful things, we're going to start with a discussion of our Z test, so Z like zebra. So let's get into it. So we have our one sample mean Z test. So in this section, we're going to review a test that is rarely used in real life applications, the one sample mean z-test, which is also known as a single sample mean z-test. This test is used when we have data from like one group and the variable that we're studying is measured on an interval or ratio level scale. So while this z-test is almost never used in real life or in clinical practice, it does serve as a convenient stepping stone into learning about the other types of t-tests that we will see used in our, different studies that we read. And when we're writing our papers, we need to understand how to interpret z-tests and t-tests. So let's see. The z-test is seldom used because it relies on an assumption that is rarely met. So in statistics, an assumption refers to conditions that have to be satisfied in order to use a particular procedure. The assumptions of the z-test would be as follows. So we would be looking at normality and independence. So in terms of normality, the z-test assumes that the true population distribution is normal. So it would look like that standard bell curve. This assumption of normality is often reasonable, and it can be checked if there are concerns about its validity. And then the assumption of independence. So the second assumption of this test is that the observations in your data set are not correlated with each other or related in any way. So this isn't as easy as to check statistically. It relies a bit on good experimental design. You have to ask yourself if it's really plausible to imagine that each observation is a completely random sample from the population that you're interested in. And then the third assumption is that you know the population's standard deviation. So this third assumption is that the true standard deviation of your population is known to your researchers. This assumption is unrealistic because in real-world data analysis, it is highly unlikely to know the standard deviation or the sigma of a population while being completely ignorant about the mean or the mu. Therefore, this assumption is almost always incorrect. So one scenario where we might justify using a z-test is when we're working with standardized test scores like IQ tests or SAT tests. These tests are often designed to follow a normal distribution with a known population mean and a known standard deviation. So if we want to determine whether a subset of that population has a distribution that is different from the overall population, we might then use a z-test. So for example, we might want to know if the graduates of a particular high school have an average SAT math score that is different from the overall population of test takers. So this would be an instance where a z-test could be appropriate because the sampling distribution would be based on the population of all SAT math scores, which are known to be normally distributed with a mean of about 500 and a standard deviation of about 100. So let's use the SAT math score sample or example to demonstrate how to conduct a single sample mean z-test by hand. So let's say that we have data from like 50 recent graduates from a large high school. And that sample has a mean SAT math score of 530 and a standard deviation of 95. And we want to know if the mean in the population of grads from this school is different from the overall population mean. So we would have our hypothesis statements as the null hypothesis equals mu or mean equals 500. The alternative or H1 hypothesis would be that the mean or the mu does not equal 500. Our sampling distribution is going to be constructed based on the known population parameters. When we first learned about sampling distributions, we learned that the sampling distribution for a mean will have a mean equal to the population mean and a standard deviation equal to sigma divided by the square root of big N. So in this case, we had the SEM equals 100 divided by the square root of 50, which equals 14.142. So in other words, if we repeatedly pulled samples of 50 from our population with a mean of 500 and a standard deviation of 100, and we recorded the mean of each sample, that distribution of sample means would have a mean of 500 and a standard deviation, or SEM, of 14.142. Then the next step is to determine how likely it would be for that population to produce a random sample of N equals 50, with a mean as or more extreme than our sample mean of 530. So because this would be a two-tailed test, this will be the area at or above 530 and the area at or below 470. That probability would be your p-value. So to determine the area covered by the p-value, we can compute what is known as a z-test statistic. The z-test statistic is essentially your z-score. It's a measure of where the sample mean is located in relation to the hypothesized population mean in standard error units. So it can be computed using this formula on page 2. So where the SEM equals essentially the standard deviation, or sigma, divided by the square root of big N. So for our specific scenario, we know that our X mean equals 530, and our null hypothesis, or mu0, equals 500, and our standard deviation, or sigma, equals 100. So we plug all that in, and we know our N equals 50, our big N. So the z-score equals 530 minus 500 divided by 100 over the square root of 50. So in our numerator, we have 530 minus 500, or 30, and then the 100 divided by the square root of 50 was our 14.142. So our z-score comes out to be 2.121. So the z-test statistic for this hypothesis test is again 2.121. Our p-value will be the area under the z-distribution that is greater than 2.121. And because it's a two-tailed test, we're also going to look at the area that is negative 2.121. This area is shown in our figure 9.2. Note that this looks very similar to our figure in 9.1, but the scale on the horizontal axis is different. So in figure 9.1, the mean was the hypothesized population mean of 500. The standard deviation was the standard error. And then in figure 9.2, the mean is 0 and the standard deviation is 1, as is always the case for a z-distribution. So let's keep going. So statisticians, they do know a lot about z-distributions, and they know that the area greater than a z-value of 2.121 is 0.017, which is 1.7%. Thus, our p-value for this test is 0.017 times 2, because it's a two-tailed test. So because we need to take into account, again, the right tail and the left tail, This will give us a p-value of 0.017 times 2, which is 0.034. So assuming that we're using the standard alpha level of 0.05, our p-value is less than the alpha level, so then we will reject the null hypothesis. This means there is evidence that the mean in our population of grads of this high school, so the mean in the population of all the graduates in our high school sample is greater than the mean of 500. So then, right, so we're rejecting the null hypothesis and we're accepting the alternative hypothesis. So again, this means there is evidence that the mean in the population of all graduates of this high school is greater than the mean of 500 from the overall population. And in statistical language, we can say that our results are statistically significant. And essentially, there's an example of how to do a z-test. That's the end of page 3. We're going to move on to page 4. So if we wanted to conduct a z-test in our JASP statistical software, we would need to have the raw data set. So for example, a data set with 1 row per observation, and your variable would need to be set up as a scale variable like interval or ratio level, and then you would just follow the usual steps. So we would go to our t-test function, we would select a 1 sample t-test, we would move our variable to the variables box, then under the test heading, we would uncheck the student t-test and just check a z-test. And we could enter our hypothesized population mean into the test value box. We could enter the known population standard deviation into the standard deviation box. And if you're conducting a one-tailed test, you would go under your alternative hypothesis, update the direction to match your alternative hypothesis. So if you follow those steps, the result will be, the 1 sample t-test, but the first column title will be the z-test, and this will be your z-test statistic. Your second column will be your p-value, and as we mentioned at the beginning of our section of chapter 9, a single sample mean z-test is not often used in the real world because the assumption of a known population standard deviation is only met in very rare occasions. So the vast majority of the time, if you need to compare the mean of one group to a specific number, you're going to use a single sample t-test, T like in Tom, and this is what we're going to jump into next. So the first section we're going to review is a 1 sample mean t-test, T like Tom. So a 1 sample mean t-test is also known as a single sample mean t-test. It's very similar to the 1 sample mean z-test that we just did. It is also used when we have data from one group and the variable that we're studying is measured on an interval or ratio level scale. The procedure is nearly identical, except the t-test uses the t-distribution, where the z-test, the z like zebra, uses the z like zebra distribution. So the 1 sample mean t-test, T like Tom, can be used when the population standard deviation is unknown. So we don't know the population standard deviation, which is usually the case. So this test, the 1 sample mean t-test, is often attributed to William Seeley Gossett. And Back in 1908, he was working as a chemist for the Guinness Brewery, and because Guinness took a dim view of their employees publishing statistical analyses, he published the work that he did under a pseudonym. So he published under a student, and so that's why this test is still known to this day. The t-test is still known as a student's t-test because of the pseudonym. And the key thing that Gossett figured, so again, his name was William Seeley Gossett. This is our student who developed the student t-test. The key thing that Gossett figured out is how we should accommodate the fact that we aren't completely sure what the true population standard deviation is. The answer is that it subtly changes the sampling distribution. So again, I'll restate that. The key thing that this student figured out is how we should accommodate the fact that we aren't sure what the standard deviation in our population is. So in the t-test, our test statistic is now called our t-statistic, and it is calculated pretty much the exact same way as the z-test statistic. So if our null hypothesis is that the true mean, or mu 0, if our null hypothesis is that the true mean of our sample is this estimation, then our estimation of the population standard deviation is this symbol. And so then our test statistic becomes known by doing the following calculation on page 4. Now the only thing that changes here in this equation for calculating the t-statistic is that instead of using a known standard deviation, we are going to use the estimated standard deviation symbol. And if this estimate has been constructed from the n observations, the big N, then the sampling distribution turns into a t-distribution with n minus 1 degrees of freedom, which is denoted as little d little f, degrees of freedom. The t-distribution, it is very similar to the normal distribution, but it does have heavier tails. So notice though that as the degrees of freedom become larger, the t-distribution starts to look more like our standard normal distribution, and we can observe that on page 5 with figures 9.3. So we have figure A and figure B listed in figure 9.3. So again, as the degrees of freedom increase from 2 to 20, then the t-distribution becomes more similar to our perfect bell curve of the z distribution. And so let's see. So let's say, for example, you have a sample size in your population of big N equals 70 million. Then your estimate of the standard deviation would be pretty much perfect, right? So you should expect that for the large N, or the big N, the t-test would behave exactly the same way as a z-test. And again, we can see that that is the case in figures 9.3, A and B. Yep, that's exactly what happens. So as you might expect, the mechanics of the t-test are almost identical to the mechanics of your z-test. So there's not much point in going through the tedious exercises of showing how to do these calculations by hand. It's pretty much identical to the calculations that we just did when conducting a Z-like zebra test, except that we use the sample standard deviation, and then we test our hypothesis using a t-distribution rather than a normal distribution. So instead of going through these calculations in tedious detail, we're just going to jump straight into showing how to do the t-test in real life, and then we're going to use JASP, the statistical software, and this comes with your dedicated analysis for conducting your t-test, and it is very flexible, so it can run lots of different types of t-tests, and it is pretty straightforward to use. So again, here's some directions. So to use JASP, statistical software, to perform a one sample mean t-test, T like Tom, you again go to the top of your settings, you select t-test, then you select one sample t-test, you move the variable you're interested in into the variables box, and then you enter your hypothesized population mean, for example, the number in your hypothesis statements, into your test value box. If you're conducting a one-tailed test, you go under alternative hypothesis, you update the direction to match your alternative hypothesis. And let's see, so we're gonna hit pause here, and we're midway on page 5. And then we're going to download the data set for Dr. Zeppo's class, and we're going to do an example in JASP.